On a modern production line, a machine detects a microscopic defect and physically rejects the part in a fraction of a second. This mechanical response relies entirely on visual data. In consumer environments, computer vision often relies on a simple assumption. You point a camera at an object and run a neural network. But deploying that logic on a chaotic manufacturing floor reliably results in catastrophic failure. Achieving production-grade reliability requires abandoning the plug-and-play illusion. Instead, automation architects rely on a foundational engineering principle, the strict architectural separation of concerns. This diagram illustrates that separation. A robust machine vision framework divides the system into three distinct pillars: device-level physical hardware, core algorithmic logic, and deployment integration. By decoupling these elements, engineers prevent hardware limitations from tangling with software execution. Developers can focus entirely on writing precise inspection policies, knowing the underlying framework will scale. In active deployment, this modularity is what makes a system economically viable. It allows facilities to reuse existing hardware configurations and rapidly accelerate secondary development when new product families are introduced to the line. Translating a messy, high-vibration factory environment into accurate, microsecond-scale decisions is not solved by algorithms alone. It requires meticulously engineering every single step of the pipeline, from the first captured photon down to physical actuation. The factory floor is defined by high speeds and variable ambient conditions. To process visual data, cameras must first eliminate motion blur entirely. Algorithmic success is entirely downstream of the physical capture. If the illumination design or the sensor's dynamic range fails to record a defect, no amount of software enhancement can compute a solution from missing data. The chosen hardware dictates the maximum achievable throughput. Inspecting CBN inserts, for example, demands high-definition visible optics simply to resolve the sub-millimeter surface defects that define a failure. But high-resolution visible optics are useless when visible contrast itself fails, a common problem when inspecting packaging seals where the materials are uniform in color. Here we see a split-screen comparison of a packaging seal. On the left, visible light yields flat, unusable data. On the right, infrared thermography solves the problem by exploiting temperature differentials, bypassing the need for visible contrast entirely. When visible light is appropriate, the geometry of the lighting strategy has an immediate, measurable impact on classification accuracy. This 3D model illustrates standard lighting creating blinding highlights on reflective parts. Dropping a diffuse dome instantly eliminates glare. Facilities embed pulse width modulation controls to adapt to varying factory conditions. These hardware compensations ensure consistent data, improving downstream detection regardless of environmental shifts. Precise control over the physical environment establishes the data baseline. The hardware dictates the absolute maximum ceiling of the software's capability. Once the physical light hits the sensor, the frame grabber and embedded camera pipelines initiate the transition from physical space into digital space. This introduces the challenge of geometric distortion. When cameras are mounted to moving robots or autonomous vehicles to observe large scenes, the perspective is inherently skewed. This diagram demonstrates inverse perspective mapping. By correcting the visual angles, skewed data mathematically morphs into a perfectly flat, top-down, two-dimensional plane, enabling the consistent measurement of planar features. After geometry is corrected, the pipeline applies image enhancement, utilizing contrast adjustment and wavelet-based frequency filtering to isolate critical details. Algorithms like CLHE, contrast-limited adaptive histogram equalization, prevent overamplification of noise, clarifying visual data before it ever reaches the inference layer. These pre-processing steps strictly govern model performance, especially when identifying subtle anomalies in complex fields like X-ray inspection and security screening. Lightweight edge computing systems rely heavily on this dedicated image enhancement pipeline. Pre-cleaning the image drastically reduces the computational burden placed on the final model. Calibration and pre-processing force a messy, real-world image into a standardized mathematical reality. Without it, the algorithm has no reliable foundation to analyze. At the algorithmic layer, engineers navigate strict constraints. They must balance latency requirements against data availability and the specific morphological complexity of the defect. This forces a choice between two primary pathways: extracting handcrafted features to feed a traditional classifier, or relying on end-to-end deep neural inference. High-speed operations, like blister pack inspection, operate on extremely low latency tolerances. These tasks require highly competitive, lightweight statistical techniques. This flow diagram tracks visual data concatenated into color channel histograms, compressed through a principal component analysis node, and plotted as distinct clusters in a support vector machine chart. This handcrafted pathway reduces training data demands and executes at ultra-fast inference speeds. Conversely, dynamic inspection tasks, like robotic pick-and-place, present a much higher morphological complexity, requiring a deep learning approach to handle variables in shape and orientation. As shown here, a convolutional neural network restricts the processing load, making deep inference feasible in real time. For embedded deployments running on lightweight hardware, like Jetson nanosystems, these model selections must be tightly tuned to the exact compute available on the board. Selecting an algorithm is never merely about maximizing raw accuracy. It is a strict engineering compromise that dictates exactly how fast the entire system can think. The final stage of the pipeline translates the digital decision back into the physical world to actuate a mechanical response. The most accurate classification model in the world provides zero value if it misses the millisecond window to physically reject a defective part on a moving belt. Guaranteeing that window requires absolute deterministic communication, moving the intelligence directly out to the edge of the network. Engineers utilize specific industrial protocols like Ethernet IP implicit cyclic exchange to securely and reliably transmit these critical signals. This protocol couples the smart cameras and vision edge compute directly to programmable logic controllers, or PLCs, bolted onto the factory floor. Human-machine interfaces are tied into this integration layer, granting human operators the ability to conduct dynamic tolerance adjustments and execute module verification without altering the underlying code. Combining vision modules with edge IoT elements eliminates network latency overhead. This deterministic handshake guarantees that the software's classification becomes an immediate, physical action. Returning to our initial framework, this diagram illustrates the complete architecture. The system is populated from physical capture, through geometric translation and algorithmic logic, straight into PLC deployment. Data flows cleanly and deterministically through this decoupled structure, maintaining speed and precision at every stage. When properly executed, this pipeline delivers measurable operational advantages. Throughput scales up, traceability becomes fully automated, and operator fatigue is drastically reduced. In automated aluminum casting, robotic inspection has proven capable of achieving high recall rates on incredibly shallow surface defects, heavily reducing material waste. In bearing inspection, combined detection and measurement modules function within microseconds, consistently meeting dimensional tolerances that manual inspection cannot reliably perceive. By integrating automated visual data with statistical process monitoring, manufacturing facilities yield a rate of reproducibility that manual quality control simply cannot sustain. Production-grade machine vision is not bought in a box. It is built through the harmonious engineering of every distinct module, turning chaotic physical environments into precise, automated outcomes.